Welcome back to the Deep Dive. Today we're taking on one of the toughest, dirtiest, and probably most overlooked engineering challenges in modern vehicle design.
Oh, for sure.
We're talking about electrifying the cement mixer truck. You see these machines everywhere, but that big system holding the concrete, the drum, it's just a brutal, non-stop test of mechanical and electrical durability.
It really is.
We are jumping into the detailed functional specifications for the pre-mixed cement system battery box, or the MSPBB.
And this deep dive, it's not just about, reviewing a component. It's about understanding the high-stakes strategic blueprint for future commercial vehicle capability.
Right.
The core mission, as we see it laid out here, is a total transition. It's moving that mixing drum drive from the traditional noisy, fuel-guzzling power takeoff system,
The old PTO.
or a hydraulic system, over to a high-voltage 400-volt electric drive. And that means engineering a battery box that is not just a power source. It has to be a structural, safe, and globally compliant system for a P2 hybrid plus ePTO platform.
Okay, let's unpack that mandate a bit. The MSPBB has to operate on a dual 24V400V platform, which right away tells you there's complexity. And the sources here are clear. This battery isn't just a tank of energy. It's the core determinant of the entire upper structure's stability. It's functional safety under ISO 26262. And, at the end of the day, whether this truck can even pass global homologation tests.
It's the highest leverage component on the entire chassis. The team has defined 4 non-negotiable key performance indicators, and they clash with each other inherently.
How so?
Well, they need maximum energy density because chassis rail space is shockingly limited on one of these precs.
I can imagine.
But at the same time, they need an extreme anti-vibration design to cope with the unique dynamics of a spinning drum full of sloshing concrete.
Right.
Then on top of that, functional safety has to hit ASIL-C levels, and finally, it has to satisfy the world's most aggressive compliance standards all at once.
So why the big rush? Why ditch the reliable, if inefficient, PTO? Why is 400-volt electrification being called the only long-term solution here?
The primary driver is, it's regulatory inevitability and it's operational economics.
Okay.
We are rapidly approaching zero-emission vehicle mandates in major global city centers. You have the EU's Stage V regulations tightening every single year, and those traditional PTO hydraulic systems, as the data in here shows, are just horribly inefficient.
How inefficient are we talking?
Often operating with an energy efficiency below 70%. All because of hydraulic losses and the constant need to just keep the main engine running.
And what does the electric drive do to that number?
It's a total game changer. Shifting to a 400-volt electric drive system, it immediately boosts that energy efficiency to do over 90%.
Wow, a 20-point jump.
That 20 percentage point jump is massive in terms of lifetime fuel savings for a fleet. But the strategic advantage goes even further. The system allows for prolonged engine-off operation.
And I imagine that's huge, especially for city construction sites where noise complaints are, a constant problem.
Absolutely. Engine-off mixing dramatically reduces 2 massive fleet costs: idle fuel consumption and noise, vibration, and harshness, the NVH during site work.
So it's quieter.
A quiet electric mixer, especially one that can run for hours on the battery alone, it basically future-proofs the vehicle against noise ordinances and those growing low-carbon construction requirements. Plus, the 400-volt system gives you the high instantaneous torque you need to start a heavy, full drum.
Something the old mechanical systems just couldn't do as well.
Exactly, not with that level of precision and control.
The development plan really reflects this high-stakes approach.
Yep.
Phase 0 is concept and modeling. Phase 1 is system architecture. Phase 2 focuses entirely on design verification and pre-testing against global benchmarks like ECER 100 and China's GB 38031. And then Phase 3 is the final production validation and getting it ready for global homologation. So they're basically reverse engineering the system from the world's toughest regulations and then working inward.
Which is the only correct strategic approach. When you're aiming for global market entry, your design constraints are always defined by the single strictest regulation in any market you plan to enter. And right now, that single strictest constraint is thermal safety.
That structural reality leads us directly into global safety. We know safety has evolved, sort of shifting from passive defense, just giving people time to evacuate, to aggressive active containment. When we analyze the sources, where is the ultimate red line drawn for physical battery safety?
Without a doubt, the ultimate design constraint comes from China's forthcoming GB 30031 2025 standard. This regulation is where the Zero Fire Challenge comes from, and it dictates the entire physical envelope of the MSPBB.
So it's the biggest factor.
It is the single biggest factor driving material choice and internal architecture, period.
The severity of this standard really needs to be underscored. So tell us precisely, what does the 2025 revision demand that previous standards didn't?
The magnitude of the change is staggering. Prior regulations, say from 2020, they typically required that after a single cell was intentionally triggered into thermal runaway.
Which is a catastrophic internal failure.
Right. After that was triggered, the rest of the pack had to hold out for just 5 minutes without any external fire or explosion. That 5 minutes was purely for occupant evacuation.
Enough time to get out of the cab and walk away.
Exactly. The 2025 revision just throws that timeline out the window. The absolute requirement now is no external fire or explosion for 120 minutes, a full 2 hours after the thermal runaway event begins.
2 hours.
2 hours. This shift fundamentally redefines safety engineering. It's no longer about escape. It's about absolute containment and managing that cascading energy release.
2 hours of thermal resistance is a profound ask. What are the mandatory engineering implications? I mean, what kind of materials do you need to achieve that kind of block?
This is why the sources state this mandate effectively bans any low-cost, non-insulated battery designs. You simply cannot stop thermal propagation, that chain reaction where one burning cell heats and triggers its neighbor without physical barriers.
So you need insulation.
To hold for 120 minutes, the design must incorporate aerospace-grade thermal insulation materials.
Things like aerogel.
Precisely. We're talking about materials like aerogel pads or specialized mica sheets that have to be inserted meticulously between individual cells and between the cell groups.
And aerogel is, what is it?
It's a silicon-based material with extremely low thermal conductivity. It's light, but it's incredibly expensive and really complex to assemble accurately. This mandated use of high-performance thermal brakes drives up the assembly cost and structural complexity instantly, but it's the non-negotiable path for satisfying GB 380-331.
Okay, so China forces the physical containment. Now let's look at the proactive side of things, early warning. Where does the European standard, UNESCO R100 Revision 3, raise the bar?
Europe focuses more on the digital intelligence and the speed of the system. While its containment time is less stringent than China's, it demands sophisticated active protection. The system must provide a 5-minute pre-warning to the driver before thermal propagation actually occurs.
So it has to be predictive, not reactive.
Exactly. It's a predictive requirement.
So how does the battery management system, the BMS, how does it achieve that 5-minute prediction window? That means it has to be measuring the precursors to a fire.
It requires dual-layer sensing and some pretty sophisticated algorithms. The BMS has to constantly monitor for off-gassing, which is the release of electrolyte vapors that always happens before a major thermal event.
So you need sensors.
You need highly sensitive gas sensors positioned strategically inside the pack. And at the same time, the system monitors the rate of temperature change, often called DTDT.
The temperature derivative, so how fast the temperature is climbing.
Right. If that rate of temperature increase goes over a certain predefined threshold, the BMS must instantly trigger that level 1 pre-warning, giving the driver those crucial 5 minutes to safely stop the vehicle and isolate the system.
And the ECER 100 also tightens up other things.
Yes, electrical safety protocols, particularly the response of the high-voltage interlock loop, or HVIL.
The HVIL, that's the safety circuit that makes sure all the high-voltage connectors are seated properly.
And ECE R100 mandates speed. Any break in that loop, say a connector vibrates loose on a construction site, must initiate a system shutdown and cut the high voltage in less than 100 milliseconds.
It's incredibly fast.
That speed requirement demands extremely responsive hardware and highly redundant sensing on every single major connector.
So we've got China setting the physical containment bar at 120 minutes, and Europe setting the digital predictive bar at 5 minutes and 100 milliseconds. What about North America and Japan? They bring in mechanical and operational hurdles.
North America, using FMVSS 305A, is really concerned with post-crash safety, things like electrical isolation and electrolyte containment. But for a heavy-duty mixer truck, the real beast is the mechanical requirement, the SAE J2380 heavy truck vibration profile.
And that's not a theoretical test.
Not at all. This is the simulation of a lifetime of abuse.
100,000 miles.
It simulates 100,000 miles of brutal over-the-road use on a heavy chassis. It defines a punishing vibration spectrum that the battery box must survive without a single weld cracking, a single fastener loosening, or any resulting electrical insulation failure. This profile demands that the box is fundamentally designed as a highly rigid, fatigue-resistant mechanical structure, not just a simple container for cells.
And then there's Japan. With GRIS 9904401, they're focused on precision monitoring and urban operation.
Correct. Japan insists on high-precision insulation monitoring that's compliant with IEC 615578. The insulation monitoring device, the IMD, has to constantly check the integrity of the HV system relative to the chassis ground, making sure no current leakage paths develop.
And if it drops below a certain level,
If the insulation resistance drops below 500 ohms per volt, the truck is faulted. It's a hard stop.
and this silent mixing requirement.
That's totally market-driven. It's because of the strict urban noise limits in Japanese construction zones. The truck has to be able to support prolonged engine-off mixing operations. This forces the electrical system designers to not only deliver the energy capacity, but also to make sure the cooling system itself operates extremely quietly.
So quiet it doesn't violate noise limits, even with the main engine off.
Exactly. This pushes the engineering toward high-efficiency, low NVH pumps and fans.
You know, when you look at the whole mandatory list of tests the pack has to pass, mechanical shock, crush, external short circuit, IP67, IP68 waterproofing, that 120-minute thermal test, it really hits home that safety isn't some bolt-on feature.
It is the absolute foundational requirement. Any failure on these pack-level or system-level tests like post-crash integrity or that required insulation resistance, it means a hard start for global market entry. The engineering strategy, therefore, has to be to design to the highest common denominator across all of these regulations from day one.
Now that the regulatory walls are clearly defined, let's talk about how the engineers actually build the hardware inside those constraints. The strategic choice of chemistry and packaging, that forms the first pillar, maximizing density while keeping it safe. And the sources here are definitive. Lithium iron phosphate, LFP, is the only recommended cell chemistry.
And that choice, despite the fact that LFP has lower inherent energy density than nickel, manganese, cobalt, or NMC, it speaks volumes about the priorities of heavy-duty commercial vehicle operation.
Right. For a passenger car, density often wins.
But for a mixer truck, safety and longevity are paramount.
Let's break that trade-off down. We know NMC might offer 180 to 240 watt-hours per kilogram, while LFP is closer to 100 and 170. Why accept that lower energy capacity?
Safety is the immediate answer. LFP provides superior thermal stability. Its thermal runaway start temperature is typically above 270 degrees Celsius.
Whereas NMC could be lower.
Much lower. But the crucial differentiator is what LFT releases during a thermal event. It releases minimal oxygen.
And oxygen feeds a fire.
Exactly. This is the only way to reliably satisfy that 120-minute GB 3808031 fire requirement. Trying to contain a high oxygen-releasing NMC chemistry for 2 hours in a high-vibration environment is just structurally and economically infeasible.
So LFP is the necessary foundation for safety compliance. What about longevity and the total cost of ownership? The TCO.
That's the second strategic driver. A commercial vehicle is expected to operate reliably for 8 to 10 years. LFP can reliably deliver 4,000 or more deep charge-discharge cycles.
Compared to what for NMC?
NMC chemistries typically only deliver 1,500 to 2,000 cycles before you see significant degradation. By using LFP, the fleet operator can be confident the battery pack will likely last the entire service life of the truck, which eliminates the enormous cost and downtime of a midlife battery replacement.
So they accept a density compromise, but they still need to hit a really challenging 160 watt-hours per kilogram pack density target. How do the engineers get back the density they lost by choosing LFP?
They recover it through radical packaging, specifically the cell-to-pack or CTP 3.0 solution.
A module-less architecture.
Exactly. Traditionally, you group cells into small modules, which are then assembled into the final pack. But modules require heavy side plates, end plates, all this extra structural hardware.
And the CTP approach just gets rid of all that redundant structure.
Precisely. By eliminating the module structure entirely and bonding the cells directly into the main enclosure and the cold plate, they boost volume utilization by anywhere from 15% to 50%.
That's a huge jump.
It is. The report confirms this cuts the overall parts count by about 40%. And fewer parts means lower assembly time, lower cost, and less potential for vibration-induced failure.
And this brings us right to the second pillar, the anti-vibration mandate. That CTP architecture actually becomes a key part of the structural resistance, doesn't it?
It absolutely does. The cells themselves become part of the structure. To achieve the necessary high anti-torsional stiffness, they use high-strength structural adhesives, specialized epoxies rated for demanding environments.
And they glue the cells in.
They bond the LFP cells directly to the structural cooling plate and the enclosure walls, creating an incredibly rigid, load-bearing honeycomb structure. This integrated structure is essential for withstanding the punishing vibrations unique to this truck.
Let's talk about that punishment. This isn't just about driving over potholes. You called it the dual excitation source problem. What are those two simultaneous sources of destructive vibration?
The first source, which all heavy trucks share, is road excitation. That's the high-frequency, random vibration 10 to 2,000 hertz caused by the engine, the transmission, rough road surfaces. You also get high-impact shock loads, maybe 50 gram for 11 milliseconds when you hit a curb or a deep rut.
Nasty, but kind of predictable. The second source is the unpredictable and low-frequency monster, drum excitation.
That's the unique challenge. The mixer drum rotates slowly, maybe 1 to 14 revolutions per minute. But concrete is a heavy, non-Newtonian material. It doesn't flow smoothly. It sloshes, it surges, it clumps up. As that heavy eccentric mass shifts, it creates a powerful, continuous, low-frequency side sway or rocking motion across the entire chassis, typically centered between 0.5 and 5 hertz.
So the battery box is being rattled at a high frequency while simultaneously being rocked back and forth powerfully at a low frequency. How do you prevent the entire box from just fracturing itself over its 10-year lifespan?
The first step is system decoupling. The engineers explicitly state that the battery box cannot be rigidly connected to the chassis frame rails. A truck frame, especially under load on uneven ground, undergoes enormous torsional twist.
A rigid mount would just tear it apart.
It would subject the battery structure to continuous destructive twisting stress.
So isolation is mandatory.
Yeah.
What specific type of isolation mounts can handle a heavy battery box and also separate those complex frequencies?
They require highly sophisticated 3D elastic isolation mounts. The recommendations include things like wire rope isolators or high damping hydraulic mounts. And the design engineering team has to tune the natural frequency of these mounts very, very carefully.
To avoid resonance.
Yes. They have to ensure that the mount's natural frequency, the frequency at which they naturally oscillate, does not overlap with the drum's primary excitation frequencies. Those are the 1 to 5 hertz sway and a secondary harmonic around 10 to 20 hertz. If those frequencies match, you hit resonance, and the pack will essentially shake itself apart.
That handles the forces acting on the box. But what about the minute internal damage from chronic microvibrations over 10 years? That internal wiring has to be highly resistant to fatigue failure.
Yes, that's where internal fatigue resistance comes in. The report mandates that cell-to-cell interconnections must use laminated flexible bus bars, not rigid plates. And these flexible bus bars have to be designed with specific stress relief loops.
And those loops absorb the vibration.
They absorb the long-term, low-amplitude microvibrations, or fretting, which would otherwise cause rigid connections like solder joints or welded tabs to fail silently due to fatigue stress over time.
All of this complex multi-frequency stress has to be simulated before you even build a prototype. I assume standard vibration testing is completely inadequate here.
Oh, you can't rely on a simple random vibration test. The structural design must be verified using a specialized finite element analysis, or FEA, called sign-on-random simulation. This is the only method that accurately models the actual conditions.
Explain sign-on-random for us. Why is it non-negotiable?
Okay, think of it this way. Standard testing might simulate driving on a gravel road, right? That's the random spectrum of noise.
Got it.
But the mixer truck has the drum running at the same time. Sign-on-random allows the engineers to mathematically stack a specific high-amplitude sine wave, that precise 1 to 5 hertz rocking motion from the drum on top of that random background road noise.
So you're simulating both at once.
Exactly. And this combined input reveals failure modes like fatigue in the bus bars or structural deformation that would be completely missed if the truck were only subjected to random shaking. It guarantees the structural integrity against that highly specific dual-source challenge.
We've built the extremely rugged, structurally sound, and thermally stable MSPBB frame. Now we move to the internal power systems, the electrical core, and the thermal management, all contained within that rigid envelope. We are working with a 24-volt, 400-volt split platform.
Right, and the 400-volt high voltage, or HV platform, is where the primary energy lives. It's nominally 384 volts DC, and for this application, the pack capacity ranges from 60 to 120 kilowatt hours. This is the power required to run the electric mixer motor.
But it's not just a steady drain, right?
No, while the continuous mixing demand is relatively low, the pack has to be able to handle extreme short-term power draws.
And what drives those power peaks?
The high torque moments. You know, when the truck arrives at the site and the concrete load is full, or when the operator needs to ramp up the drum speed suddenly to agitate the mix, or during that final high-speed discharge.
So it needs a lot of power on tap.
Exactly. The report specifies the pack has to be capable of a continuous 1C discharge, but must handle peak discharge rates of 2C to 3C for those crucial maneuvers. That peak power requirement for loading and unloading is clocked at a demanding 60 kilowatts.
Okay, that's the muscle. Now, the 24-volt low voltage, or LV side, is the brain. It's standard commercial vehicle architecture, but it's critical.
It is the lifeblood of the control system. The 24-volt bus supplies power to the BMS master, the cooling pumps, the cooling fans, and the contactor coils, the actual mechanisms that physically connect and disconnect the 400-volt power.
And this all runs off a DC-DC converter.
Right. Since the 400-volt battery system is the primary energy source, it needs an isolated full-bridge DC-DC converter to step down the high voltage to the required 24 volts.
So why is the functional safety rating of that DC-DC converter so crucial?
Because of the catastrophe that follows if it fails, the report mandates that the DC-DC converter must be rated to ASIL-B. If this converter fails, the 24-volt system dies.
And if the 24-volt system dies?
The cooling pumps stop, the fans stop, and the BMS master loses control. This failure chain immediately leads to an uncontrollable thermal event because the ability to manage temperature is completely lost. So the continuous availability of that 24-volt power, and by extension, the DC-DC converter, is a high-stakes safety requirement.
The functional chain dictates the safety level. Okay, moving to thermal management. Liquid cooling is mandatory. Wind cooling is out. They're using microchannel aluminum cold plates. What are the engineering goals for keeping the cells healthy in this hot, strenuous environment?
The primary mission is maintaining the cell operating temperature within a very tight optimal window of 15 to 35 degrees Celsius. But the most challenging technical requirement for maximizing pack life and consistency is ensuring temperature uniformity. The maximum temperature difference, the delta T, across the entire pack must be held to less than 5 degrees Celsius.
Less than 5 degrees C difference across a pack, they could have 120 kilowatt hours of cells, likely stretching across a huge area of the chassis rail. That sounds incredibly difficult.
It is.
Why is that uniformity so important, and what makes it so hard to achieve?
Uniformity, or low delta T, is essential because lithium-ion cells degrade at different rates when they operate at different temperatures. If one corner of the pack runs at 40 degrees C and another runs at 20 degrees C, the hotter cells will age faster, creating imbalance and significantly shortening the useful life of the entire pack.
And the technical hurdle is the plumbing, basically.
It's all about extremely precise flow management. You need complex internal manifolding within the cold plate to ensure the coolant reaches every cell with an equal thermal effect to avoid hotspots. This design complexity, along with the need to overcome hydraulic resistance across those long internal pathways, it necessitates a high flow rate. The sources specify that for heavy-duty packs, the optimal coolant flow rate has to be maintained at 15 to 18 liters per minute. That needs a powerful 24-volt supplied pump, leading to a constant trade-off between the power consumed by the pump and the necessary cooling performance.
We talked about LFP chemistry and aerogel for thermal runaway prevention. But if a failure does happen, you need containment and venting. How is that venting physically designed?
Right. Since the pack has to contain the thermal event for 120 minutes, that energy has to go somewhere. The report mandates dedicated directional pressure relief valves and exhaust channels. And the entire venting path must be engineered using computational fluid dynamics, or CFD simulation.
So using software to map the flow of gas?
Yes, to map the flow and temperature of the extremely hot, high-pressure gases that are released by the failed cells. The design has to guarantee these gases are vented safely downward and outward, explicitly away from any critical components.
Like the cab.
Away from the cab, the driver, any exposed hydraulic tanks, and, critically, the rubber tires, which are highly vulnerable to high heat. It's not enough to vent. You have to vent safely.
Now let's talk about the absolute fail-safe scenario, which is totally unique to this truck. Concrete clogging. The hazard analysis and risk assessment. The here ago classified the loss of mixing power during a full load as an ASIL-C event.
This is a critical insight into commercial vehicle design priorities. While it's not immediately life-threatening, concrete solidifying in the drum is categorized as a severe economic loss.
Tens of thousands of dollars, easily.
Right, in drum replacement and downtime. And it compromises stability if the load solidifies unevenly. So the safety goal here is not merely to cut power when something goes wrong, it is to guarantee the availability of the stirring function.
Availability over isolation.
Yeah.
So how do they achieve that availability?
The first layer is software. The system has to be programmed to enter a limp-home mode for non-fatal faults, where power is severely limited, but the drum keeps turning. But the ultimate physical solution for the customer's clogging anxiety is the mandated external emergency drive interface.
This sounds like a jumpstart point, but for 400-volt power.
That's exactly what it is. The MSPBB design must integrate a standardized, robust, external 400-volt or 24-volt input interface. If the main battery isolates due to a major internal fault, say a pyro fuse blows or the main contactors weld shut, a rescue truck or an external power source can plug directly into this interface.
And it bypasses the main battery.
It bypasses the faulty internal HV components and supplies power straight to the mixer motor, allowing the operator to discharge the concrete before it hardens. This redundancy is perhaps the most appreciated physical feature by any fleet operator.
This system is a marvel of redundant hardware, but it's useless without a brilliant digital core to manage it. So let's focus on the battery management system, the BMS. We know it uses a master-slave architecture, a BMU master and CSU slave boards. What are the specialized demands for the BMS software and hardware loops in this high ASIL environment?
The software demands are high. Beyond just standard cell voltage and temperature monitoring, the BMS has to run advanced algorithms, typically using a Kalman filter, to provide highly accurate state of charge, SOC, and state of health, SOH, estimates.
And that's tricky here, right?
Very tricky, because the mixer's pulsing power demands make the SOC estimation extremely complex. Furthermore, the BMS has to provide active cell balancing, typically rated at 200 milliamps or more, to compensate for any minor charge differences caused by those delta-T variations across the pack.
Let's discuss the critical hardware safety loops, the mechanisms that physically enforce safety, independent of any software. How is ASIL-D protection engineered?
ASIL-D protection means that any single point of failure must not lead to uncontrollable high-voltage output. This requires a three-layered approach. The first layer is basic isolation. Dual main contactors on both the positive and negative high voltage lines, plus a pre-charged contactor. But contactors can fail.
They can weld shut, which completely defeats the purpose of isolation.
Which is why the report mandates the critical failsafe. Pyro fuses, or pyrotechnic fuses.
Explosives, basically.
They are non-redundant, single-use, explosive devices designed to physically sever the high current path in milliseconds. They act as the ultimate failsafe against contactor welding. If the BMS detects a fault that the contactors fail to clear, it triggers the pyro fuse.
Okay, that's layer one. Contactor failure triggers the pyro fuse. What's layer two? Protecting against the BMS master itself failing.
Layer two is the independent hardware protection circuit. If the main battery management unit, the BMU software, freezes or crashes or just goes haywire.
Which could leave the contactors closed.
Right. If that happens, an independent, simple hardware circuit has to be monitoring critical parameters like overvoltage, undervoltage, and overcurrent. If these limits are exceeded, the simple, non-programmable circuit must trigger the isolation systems, including the pyro fuse, completely independent of the main software.
And layer three is the response time for the high-voltage interlock loop.
Correct. The HVIL break has to cut power in under 100 milliseconds. This three-layer redundancy ensures that even if the software fails and the primary hardware fails, the system still manages to isolate itself using that physical pyro fuse. This complexity is what ASIL-D engineering demands.
Now let's turn to what seems like the Achilles heel of heavy-duty digital systems, communication. Heavy trucks rely on the standard CAN bus protocol, SAE J1939, but the sources state that standard J1939 is functionally unsafe for this application. Why does it fail the ASIL test?
This is perhaps the most critical technical realization in the entire report. Standard J1939 is built for data throughput, but not for safety integrity and high-noise, high EMI environments like a heavy-duty chassis.
So the data can get corrupted.
In that kind of environment, data messages like the critical state of charge or temperature readings can be corrupted during transmission, lost entirely, or even worse, delayed or replayed without the recipient, the vehicle control unit or VCU, ever knowing that anything went wrong.
And if the VCU gets a corrupted message telling it the battery temperature is fine, when it's actually spiking, that's catastrophic.
Precisely. That's why the system must implement the safety extension. SAE J1939-76. This protocol is the mandatory upgrade for functional safety certification. J1939-76 introduces safety data messages, or SDMs, to solve the integrity problem.
And how do those safety data messages solve it?
They use two key mechanisms baked into every single message. First, the CRC checksum, which is a cyclic redundancy check. This is a mathematical signature attached to the data packet.
Okay.
When the VCU receives the packet, it runs the same calculation. If its calculated signature doesn't match the received signature, the VCU knows the data was corrupted in transit and it just throws it out.
That handles corruption. What about delay or replay attacks where a stale message is repeated?
That's where the second mechanism, the rolling counter or sequence counter, comes in. Every message transmitted carries a sequential number. For instance, the first message is 1, the next is 2, the next is 3. If the VCU receives message number 5 when it was expecting number 3, or if it receives number 3 twice, it immediately knows the message is stale, delayed, or an unauthorized replay, and it treats it as a fault.
So it's checking both correctness and timeliness.
Exactly. The combination of the CRC checksum and the rolling counter ensures both the correctness and the timeliness of all critical safety data.
This detail on J1939-76 really highlights that achieving ASIL certification is about baking safety into the software layer, not just the hardware. And finally, all these complex faults have to translate back into the standard language of the vehicle.
Yes, through robust diagnostic linkage. All the highly technical internal BMS fault cell imbalance, high DTDT, contactor resistance limits, they all have to map directly into standardized J1939 DM1 diagnostic messages. This ensures the VCU understands whether to trigger an amber warning light for a non-fatal limp home mode or a red stop light for a critical immediate isolation. The BMS is performing an essential translation service for the entire truck network.
The blueprint is complete, but success hinges entirely on verifying that the system can actually survive its intended lifespan. The development validation plan, the DVP&R that's outlined in the sources well, it's truly immense. It's designed to simulate 8 to 10 years of relentless abuse in just a few weeks of testing.
This level of rigor is necessary when failure means potential concrete solidification or a high-voltage fire. The mechanical reliability testing goes far, far beyond standard automotive validation.
We've talked about the SAE J2380 random vibration profile. What specific tests are layered on top of that?
They intensify the base test. They run the random vibration profile for 100 continuous hours and increase the severity spectrum, particularly on the z-axis, the vertical load, to simulate that persistent hammering on the battery mounts. But crucially, they mandate the specific low-frequency sine sweep test.
And that's the test targeting the mixer drum's resonance.
Absolutely. They sweep the assembly from 1 Hz up to 15 Hz to find the natural frequency of the battery pack and its isolation mounts. This test will expose any flaws in the isolation design. If the mounts transmit too much of the drum's energy, the structural adhesives or bus bars will fail due to resonance fatigue.
And then there's the bottom ball impact testing,
which simulates the real-world scenario of the truck driving over large construction site debris, like rocks or reinforcing bar ends. The enclosure has to be able to absorb that impact without breaching the thermal integrity or the IP sealing.
On the safety front, the thermal propagation test is really the moment of truth for the materials they chose.
The full-power thermal propagation test against the GB38 Loyo 31 standard is completely non-negotiable. They have to intentionally induce thermal runaway in a fully charged cell, often located in the hardest-to-cool center of the pack, and then prove that no external fire or explosion occurs for a full 120 minutes.
It validates the whole strategy.
It validates the strategic decision to use LFP and the costly incorporation of aerogel or mica insulation.
Finally, the environmental endurance tests. These are designed to mimic the truck's harsh daily life, particularly the cleaning process. The IP testing isn't just basic water immersion, it's IP69K.
IP69K is a heavy-duty requirement specifically for vehicles that undergo regular high-pressure, high-temperature washdowns. Cement mixer trucks have to be aggressively cleaned every single day to prevent concrete from setting on the chassis.
So they blast it with hot water.
This test involves blasting the entire battery box with 80 degrees Celsius high-pressure water jets. The seals, the glands, the high-voltage connectors, they all have to withstand that daily thermal and pressure shock without any moisture ingress that could compromise the insulation resistance.
And the material durability for global markets, spanning extreme climates.
That requires rapid thermal cycling, moving the pack rapidly from an extreme cold soak at -40 Celsius to a high operational temperature of +85 Celsius. This verifies material stability and seal integrity against expansion and contraction cycles. And for corrosion resistance, the requirement is 1,000 hours of neutral salt spray testing.
To make sure it doesn't rust away.
It ensures the aluminum alloy enclosure and the fasteners won't degrade from road salt exposure in winter climates or coastal environments.
This strategic deep dive provides an exhaustive list of requirements. If we were to summarize this entire strategic engineering analysis for an executive audience, what are the 3 non-negotiable strategic decisions the engineering team has to hold firm on to guarantee success?
The final executive summary is very clear on the foundation of the capability development.
Number 1, the material strategy and packaging.
LFP and cell-to-pack. This is the only pathway that successfully resolves the 3 competing constraints: cost control, the mandatory 120-minute safety compliance, and achieving adequate energy density in that limited chassis space. This is the non-negotiable physical architecture.
Number 2, the communication and digital control structure.
SAE 1939-76. Functional safety is paramount. Integrating the J1939-76 protocol from day one is the essential architectural decision that guarantees the necessary data integrity via CRC checksums and rolling counters, making ASIL certification in a noisy environment possible.
And number 3, the critical operational assurance feature.
The external emergency drive interface. This is the definitive physical solution to solving the customer's greatest operational fear: concrete clogging. It transforms a potentially catastrophic, expensive vehicle breakdown into a temporary, manageable event, providing enormous confidence to fleet managers.
This has been a fascinating look behind the heavy-duty curtain. The MSPBB is clearly far more than just a battery. It is a complex engineering intersection of global regulation, structural dynamics tailored for a unique mechanical environment, and highly redundant energy and safety systems.
It really reveals the true magnitude of electrifying commercial vehicles. They had to solve the highly complex dual-source vibration problem, the road rattle and the drum sway, while simultaneously eliminating the single catastrophic failure mode of concrete solidification, all under the shadow of that 120-minute fire containment rule.
So we'll leave you with this final thought that addresses the engineering trade-offs inherent in this strategy. The source material classified the continuous stirring function as an ASIL-C safety requirement, meaning it demands high availability and redundancy. Now, achieving this safety level requires allocating a specific, non-touchable power reserve for that limp home mode, even when the rest of the pack capacity might be needed for driving. What specific engineering trade-offs do you think were ultimately made in the cell sizing and pack design to ensure that mandated ASIL-C safety reserve was guaranteed? And how heavily did that choice limit the maximum usable energy capacity of the pack? This is where the cost of operational safety is quantified. Something to mull over until our next deep dive. Thanks for joining us. We'll catch you next time.